Today, I am presenting our EPC proposal for a factory rooftop solar PV plant. This system has a DC capacity of 1,298, 7 kilowatts peak, and an AC capacity of 1,050 kilowatts. We are providing a comprehensive package that covers all aspects, including technical details, commercial considerations, health, safety, and environment measures, work method statements, inspection and test plans, risk management, lockout-tagout procedures, as well as testing, commissioning, and post-completion operations and maintenance. The expected annual energy generation at P50 is 2,066 megawatt-hours, ensuring reliable performance. This proposal is issued for client evaluation as of July 2026. Here's an overview of the submission package for the rooftop solar PV proposal designed for the factory EPC project. This integrated system covers multiple key components, including rooftop PV modules, DC/AC conversion, point of connection, monitoring, and essential safety infrastructure. We are proposing a total of 1,998 PV modules arranged into 111 strings, supported by 7 inverters, each rated at 150 kilowatts. The DC to AC ratio is carefully calculated at 1.24 to optimize system performance. The setup involves a grid-connected rooftop installation spanning the office area and 2 production sheet roof sections. An outdoor inverter and AC distribution board station will be connected to the existing indoor solar main distribution board at 400 volts. Additionally, the scope offers enhanced features such as warehouse controls, cybersecurity measures, backup monitoring, zero export limits, and a full range of testing processes from CXL1 to CXL6. The bill of quantities aligns with the detailed Excel package, with a total cost of approximately 18,325,000,000 rupiah, including VAT. This comprehensive approach ensures reliability, safety, and compliance for the solar installation. Here we have the integrated deliverable map for the rooftop solar PV proposal targeting factory EPC projects. This map outlines the core components starting with the front matter, followed by 4 key packages labeled A through D. Package A covers the design basis, which includes essential documents like PVsyst simulations, single-line diagrams, detailed layouts, and technical specifications. These form the foundation for our design accuracy. Moving to Package B, we focus on the commercial bill of quantities. Here, we include the original BOQ along with any necessary added rows to capture all required materials and costs thoroughly. Package C addresses execution controls. This package contains the warehouse management system data, inspection and test plans, risk registers, lockout-tagout procedures, and other controls to ensure safe, efficient execution. Finally, Package D spans from factory acceptance testing through to project handover and project management levels 1 through 6. This ensures a seamless transition from completion to handover. The table summarizes client evaluation outputs across 3 formats. PowerPoint supports a visual proposal with installation methods, HSE capabilities, and commissioning schedules. Excel consolidates all quantitative data including BOQs, formula sheets, references, and control matrices. The handover intent serves as a single synchronized baseline for both technical and commercial evaluation, providing clarity and alignment between all stakeholders. On this slide, we review the proposal's compliance with the submission checklist to ensure everything needed is accounted for. Starting with the proposal and pricing, you'll see it's fully included in both the PowerPoint and the BOQ Excel file, showing all totals clearly with ex-VAT, VAT, and inclusive VAT amounts. The Bill of Materials, or BOQ, maintains its original structure, with any required additions clearly flagged in red for easy identification. The project schedule is comprehensive, covering every stage from pre-mobilization through procurement, installation, commissioning, and final handover. We've also provided detailed layout and single-line diagrams along with essential concept drawings, addressing all safety and accessibility features such as inverter stations, hard barricades, lifelines, ladders, skylight covers, handrails, and walkways. Finally, the PVsyst analysis with P90 performance metrics is included, alongside a thorough operations and maintenance plan featuring preventive maintenance and reporting schedules. This ensures the system proposal is complete and ready for implementation with all required components identified. Here we have the executive summary highlighting the key technical and commercial values of the rooftop solar PV proposal for the factory. The system is designed with a DC capacity of 1,298.70 kWp and an AC capacity of 1,050 kWac, utilizing 1,998 high-efficiency 650 watt modules arranged into 111 strings of 18 modules each. The energy yield is impressive, with an expected P50 yield of 2,066 MWh per year and a P90 yield of 1,900 MWh per year, indicating reliable performance even under less favorable conditions. The performance ratio stands at 81.68%, showing the system's efficiency in converting solar energy into usable electricity. Additionally, the solar fraction is estimated at 22.62%, meaning nearly a quarter of the factory's energy needs can be met by this installation. On the commercial side, the total price excluding VAT is approximately 16.5 billion Indonesian rupiah, with VAT at 11%, bringing the total investment including VAT to around 18.3 billion rupiah. This translates to a cost of 14,111 IDR per watt peak, which is competitive for this scale of project. Finally, the project plan ensures the factory rooftop PV is constructed with dedicated access, safety zones, and proper equipment placement to maintain operational safety and efficiency throughout the installation and beyond. On this slide, we define the scope and boundaries of the rooftop solar PV project for the factory EPC proposal. The main scope includes detailed engineering, procurement, construction, quality assurance, health and safety, testing, commissioning, handover, and readiness for operations and maintenance. The plant covers all key components such as modules, mounting structures, DC strings, inverters, AC distribution boards, point of connection integration, monitoring systems, weather stations, CCTV, earthing, lightning protection, and safety systems. The connection to the existing low-voltage main distribution panel depends on an approved shutdown window and thorough electrical reviews including short circuit, selectivity, and arc flash assessments, as well as a final site survey. Final quantities, cable routing, and structural fixing methods will be confirmed during detailed engineering. We also have clear inclusions like walkway safety features, monitoring and cybersecurity, and comprehensive testing and maintenance schedules. Exclusions or items to confirm include existing roof defects not caused by our works, final commercial export policies, and any hidden retrofits beyond approved surveys. Overall, the project boundary encompasses the rooftop array, inverter station, AC route, and point of connection, establishing a clear framework for what our proposal covers. Here we have a comprehensive overview of the system architecture for the rooftop solar PV installation proposed for the factory EPC project. The system starts with a large PV array comprising 1,998 modules organized into 111 DC strings. These strings feed into 7 inverters, each rated at 150 kilowatts, converting the direct current to alternating current. From there, the power flows through a 2,500 amp AC distribution board and then a solar main distribution board, which integrates with the existing low-voltage main distribution panel operating at 400 volts. This setup supports the factory load while operating in parallel with the grid. Safety and monitoring are thoroughly addressed with a multi-layered approach. The control layer includes monitoring, zero export power control, weather stations, and cybersecurity gateways. The safety layer incorporates lockout/tagout procedures, earthing, fire protection, and physical barriers, and the test layer outlines rigorous commissioning stages from factory acceptance through to handover. Altogether, this design ensures an integrated electrical, monitoring, and roof safety system tailored for efficient and secure operation. On this slide, we have the table of contents for Part 1 of our rooftop solar PV proposal for the factory EPC. Here, I've outlined 5 key sections that will guide us through the project details. First, Section A covers the project and scope, where we'll define the boundaries, design basis, layout, single-line diagram, and the deliverables. Then in Section B, we'll dive into PV sizing and yield, discussing the assumptions we made in PVsyst, the P50 and P90 energy estimates, as well as losses and overall performance basis. Section C focuses on the PV module, string configuration, and the DC system, including module specifications, stringing strategy, kWac, DC cable checks, and installation considerations. Moving on to Section D, we address the AC system elements like inverter currents, distribution boards, point of connection, earthing, lightning protection, and AC protection measures. Finally, Section E covers monitoring, power plant controller, cybersecurity, and CCTV, detailing the network architecture, meters, weather stations, data paths, and secure access. This structure will ensure a comprehensive overview and clear understanding of the proposal. Now, let's focus on Part 2 of our table of contents, which covers several critical aspects of the rooftop solar PV project for the factory EPC proposal. We begin with rooftop access and HSE measures, including lifelines, guardrails, skylight covers, walkways, ladders, and work-at-height controls to ensure safety. Next, the work method statement outlines the step-by-step installation and site execution process, providing a clear roadmap for the project team. Following that is the ITP and QA/QC section, which defines hold and witness points, documentation, and inspection criteria to maintain quality standards. Then, we have the risk register and LOTO procedures, focusing on risk assessment, mitigation strategies, isolation boundaries, and energization safety. Testing and commissioning will cover all stages from factory acceptance tests to final handover, preventive maintenance, and post-completion activities. Lastly, the BOQ and submission readiness section ensures synchronized pricing, scheduling, operations, maintenance, and the evaluation checklist are fully prepared for a smooth project execution. Each of these sections is essential to delivering a safe, efficient, and high-quality solar installation. On this slide, we're focusing on the essential abbreviations and key terms you'll encounter throughout the project, especially in the areas of PV design, bill of quantities, monitoring, and operations. Starting with the PV and performance terms, it's important to know what kWp and kWac indicate. They represent the peak power capacity and the AC output respectively. Terms like STC refer to standard test conditions, while VOC and VMP relate to voltage measurements under specific circumstances. Parameters such as P50 and P90 illustrate the projected energy production with varying confidence levels, and PR stands for performance ratio, a critical efficiency metric. Moving to electrical and protection terminology, acronyms like ACDB and MDB refer to types of distribution boards, while devices like ACB and MCCB are crucial circuit breakers. LSIG and SPD cover protective settings and surge protection devices. In the monitoring and control section, terms like SCADA, data logger, and VPN describe the systems and technologies used to oversee and secure the plant's operation. Lastly, for execution and handover, acronyms such as EPC, BOQ, and FAT highlight key activities and documents in the project lifecycle, while CXL1 through CXL6 represent different commissioning levels to ensure everything functions correctly before final handover. Understanding these abbreviations is fundamental for effectively navigating the entire rooftop solar PV EPC proposal and related documentation. On this slide, we're focusing on important abbreviations and key terms related to rooftop solar PV systems in our factory EPC proposal. First, PV stands for photovoltaic, which is the core solar technology using modules and DC strings to generate power. The term kWp, or kilowatt peak, refers to the maximum DC output of the PV array under standard test conditions, and for our proposal, that rating is 1,298, 70 kWp. On the other hand, kWac represents the AC output after inversion, which is slightly lower here at 1,050 kWac. Standard test conditions, or STC, give us a consistent baseline by defining module ratings at 1,000 watts per square meter, 25 degrees Celsius cell temperature, and an air mass of 1.5. VOC and VMP indicate the open circuit and maximum power point voltages, essential for verifying string voltages and ensuring the system stays within safe operational limits. Similarly, ISC and IMP refer to short circuit and maximum power point currents, which guide our sizing for connectors, cables, and protection devices. When evaluating energy yield, P50 and P90 values are key benchmarks. P50 is the expected central yield, while P90 offers a more conservative estimate for client and financial assessments. Lastly, the performance ratio, or PR, is our main performance indicator, showing the quality of PV production and how effectively the system is operated and maintained. This set of terms provides a solid foundation for understanding the proposal's technical and performance details. Here we have key abbreviations and terms related to electrical systems and protection, specifically for our rooftop solar PV proposal for the factory EPC project. Starting with ACDB, which stands for AC Distribution Board. This is the outdoor solar board that receives 7 inverter feeders and provides the main AC output protection. Next is the MDB, or Main Distribution Board, acting as the interconnection panel between the ACDB and the existing factory's low-voltage main distribution panel, or LVMDP. The LVMDP is the existing 400-volt panel where the solar system physically connects. The point of connection, also called POC or POI, marks the formal electrical boundary between the PV plant and the facility's existing electrical system. For protection, we use devices like the ACB or MCCB air or molded case circuit breakers at both the main and inverter feeder levels to ensure safe switching and fault protection. The LSIG functions on these breakers allow for selective protection coordination by detecting long, short, instantaneous, and ground faults. The SPD, or surge protection device, safeguards the AC, DC, and communication systems from transient overvoltages. Finally, relays labeled 27, 59, and 81 provide grid compliance protection by monitoring for under and over voltage, as well as under and over frequency conditions. Understanding these terms ensures clear communication and effective implementation of the solar PV system. Here we have some important abbreviations and key terms related to monitoring and control in our rooftop solar PV proposal. Starting with PPC, the power plant controller, which plays a crucial role in managing export limitations and ensuring compliance with grid requirements. Then there's the power quality meter, or PQM, that monitors events like harmonics and voltage quality at the point of connection. The multifunction meter measures key operational parameters such as power, energy, voltage, and current, helping with reporting and analysis. SCADA is our supervisory control system that handles data collection, alarms, and local supervision. The gateway acts as a secure interface between the plant's logging system and the approved monitoring platform. For communication security, we use VPN or MTLS protocols to ensure encrypted and safe data exchange without exposing the system to cloud vulnerabilities. We also implement VLAN, or LAN segmentation, to separate different network traffic, enhancing security for operations. Finally, CCTV and NVR setups provide surveillance of critical areas like inverter stations and roof access, ensuring safety and monitoring. Understanding these components is key to effective monitoring and control of the solar system. Here we have some important abbreviations and key terms that are essential for understanding the rooftop solar PV factory EPC proposal. First, EPC stands for Engineering, Procurement, and Construction, which means turnkey delivery covering everything from design to procurement, installation, testing, and handover. The BOQ or BOM refers to the bill of quantity or bill of material, providing a priced commercial schedule aligned with our project documentation. The WMS, or Work Method Statement, outlines the step-by-step safe procedures for installation, testing, and energization tasks. Inspection and quality control are managed through ITP or ITC, meaning Inspection Test Plan or Checklist, which specifies acceptance criteria and records key checks. Safety is a priority, with LOTO lockout/tagout, ensuring isolation to prevent accidental energization during work. Permits like PTW and WH, permit to work and work at height, regulate high-risk activities such as rooftop and electrical work. Testing phases include FAT and SAT, factory and site acceptance tests, which are formal processes to verify equipment and site functionality. Finally, the commissioning sequence, labeled from CXL1 through CXL6, covers all steps from initial testing through to final handover and preventive maintenance. Understanding these terms is crucial for following the project workflow clearly and safely. On this slide, we cover the design basis and applicable requirements for the rooftop solar PV system within the factory EPC proposal. First, under solar PV, we follow key international standards like IEC 61215 and IEC 61730 for the modules, along with IEC 62548 and 60364 to ensure safe and proper installation practices. Moving to performance monitoring, The system will comply with IEC 61724-1 for measurement accuracy, using logger and gateway data paths, integrated weather stations, and a comprehensive alarm and reporting setup. For rooftop safety, strict fall protection measures are in place for any work conducted above 1.5 meters, including lifelines, guardrails, skylight covers, designated walkways, and ladders, all supported by a detailed rescue plan. Electrical protection involves coordination between ACB and MCCB devices. Key protective relays like 27, 59, and 81 variants, surge protection devices, and clearly marked emergency stops together with lockout, tagout, and arc flash labels. Finally, construction health, safety, and environment requirements are addressed through a site-specific HSE plan that includes method statements, risk assessments, permit-to-work processes, emergency response plans, and all necessary HSE deliverables to ensure a safe working environment throughout the project. Here we have the key project data at a glance for our rooftop solar PV proposal for the factory EPC. The scope focuses on installing a large PV array consisting of 1,998 modules, each rated at 650 watts, making for a total DC capacity of nearly 1,300 kilowatts. These are N-type bifacial dual-glass modules, chosen for their efficiency and durability. On the AC side, the system uses 7-string inverters, each rated at 150 kilowatts, delivering a combined capacity of 1,050 kilowatts. The array is organized into 111 strings with 18 modules each, distributed mostly across the offices and production areas. Based on PVsyst modeling, we expect an annual energy output of just over 2 million kilowatt hours, with a performance ratio indicating efficient system operation at around 81.7%. The layout also includes a detailed tender plan considering roof blocks, access routes, equipment placement, and the point of connection, ensuring a comprehensive and practical design for this factory site in Indonesia. Here, we're focusing on PV sizing and yield, which are crucial for optimizing solar energy systems. We start with the energy model, which helps us understand how much energy the system is expected to generate under different conditions. Module capacity is another key factor. It determines the total potential output of the solar panels. We also look at P50 and P90 performance metrics, which represent the expected energy production levels with 50% and 90% confidence, respectively. These provide a reliable basis for assessing system performance. Finally, all of these analyses are compiled into the client evaluation package, ensuring that the client gets a comprehensive understanding of the system's expected performance. Here we have the energy model and design assumptions focusing on the PV sizing and yield for the rooftop solar installation proposed for the factory. The PVsyst simulation is based on a grid-connected system with 3 different roof orientations, each with a low tilt angle of around 3 degrees and azimuths facing north, south, and east. The system's nominal power is 1,299 kilowatts DC and 1,050 kilowatts AC, which means the DC to AC ratio is about 1:24. This ratio helps optimize production and efficiency. We've also incorporated the user load profile into the simulation, which shows a solar fraction of approximately 22.6%. This means nearly a quarter of the factory's energy needs can be met by this solar setup. Additionally, if grid export is permitted, the system could potentially inject around 690 megawatt hours into the grid annually. Because of this possibility, including PPC or zero export control in the bill of quantities, is essential to maintain compliance and operational flexibility. Here we have the main results from the PVsyst analysis for the rooftop solar PV system proposed for the factory EPC project. The key metrics include the annual produced energy of just over 2 million kilowatt hours, with about 1.38 million kilowatt hours directly consumed by the user. The remaining 690,000 kilowatt hours represents energy injected back into the grid. The specific production is 1,591 kilowatt hours per kilowatt peak per year, which gives a solid indication of system efficiency. The performance ratio is 81.68%, reflecting how effectively the system converts available solar energy into electricity. Additionally, the solar fraction is 22.62%, meaning nearly a quarter of the total energy demand can be met by the solar system. We also calculate the export share, which is the proportion of energy sent back to the grid compared to the total annual production. Here, it stands at 33.41%. But remember that zero export options are included in the design to manage regulatory or contractual limits on energy export if needed. This comprehensive overview helps us understand both the system's output and its integration with the factory's energy use. Here we have the PVsyst loss diagram and its design implications for PV sizing and yield. Understanding the main losses is crucial for optimizing the system's performance. These losses include temperature effects, soiling, near shading, DC wiring, inverter efficiency, and AC ohmic loss. For soiling, it's essential to implement a practical cleaning system with roof access, water points, and a regular preventive maintenance schedule to minimize yield reduction. Cable losses should be tightly controlled by accurately measuring the cable routes, organizing cable grouping, and verifying voltage drop to avoid unnecessary power loss. Lastly, proper inverter ventilation and outdoor equipment layout are vital to prevent heat buildup and ensure easy service access. While near shading conditions must be carefully maintained to avoid new shadows from equipment like guardrails or cable trays during the final design phase. Here we have the P50 and P90 energy evaluation for the rooftop solar PV system proposed for the factory EPC project. The P50 value represents the central estimate of annual energy yield, which in this case is 2,066 MWh. The P90 value is more conservative, set at 1,900 MWh, meaning it accounts for uncertainties and ensures the system will produce at least this much energy 90% of the time. The P90 factor here is about 91.97%, which means there's an 8.03% buffer below the P50 estimate to provide a conservative performance outlook. This is crucial for evaluating financial risk and performance guarantees. It's important to note that the final performance guarantees must be based on agreed test conditions, including accurate meter readings and weather data corrections to reflect true system output. This approach gives confidence that the system will meet expectations even under less favorable conditions. Here we focus on the PV module, the string, and the DC system. This includes reviewing the module datasheet, which is essential to understand the specifications and performance parameters of the solar panels. We also cover stringing, which refers to how individual modules are connected electrically, affecting the overall system voltage and current. It's crucial to perform thorough DC voltage, current, and cable checks to ensure system safety and efficiency. Lastly, we provide the client evaluation package, which summarizes all these technical details for client review and approval. Here we have a detailed snapshot of the key values from the PV module datasheet for the Jinko 650 to 670 Watt N-type bifacial module. These values form the basis of our design and are critical for understanding the system's performance. Starting with the module rating, it's rated at 650 watts peak on the front side under standard test conditions. The maximum power voltage and current are 42.57 volts and 15.27 amps respectively, while the open circuit voltage stands at 50.26 volts and the short circuit current at 15.98 amps. The physical dimensions of the module are 2,382 by 1134 by 30 millimeters with a weight of 32.5 kilograms. Our system voltage is set at 1,500 volts DC, paired with a 35 amp fuse for protection. Temperature coefficients indicate how performance changes with temperature. We see a reduction in maximum power by 0.26% per degree Celsius, a drop in open circuit voltage of 0.24% per degree, and an increase in short circuit current by 0.046% per degree Celsius. Finally, it's essential that the final procurement follows the approved vendor route using the confirmed data sheet and model. Also, the connector type must remain consistent from the module through the string cable all the way to the inverter to ensure compatibility and reliable operation. Here we calculate the DC plant capacity and the total module area for our rooftop solar PV system. Starting with the DC capacity, we multiply the number of modules by the power rating per module. Here, with 1,998 modules, each rated at 650 watts peak, we get a total DC capacity of approximately 1,298. 7 kilowatts peak. Moving on to the total module area, we calculate the area of a single module by multiplying its length and width, which gives us about 2.7 square meters. Multiplying this by the total number of modules, the total collector area comes to around 5,397 square meters. Lastly, we consider the total weight of all modules, which is nearly 65,000 kilograms, not including the mounting rails, cables, and walkways. This weight is critical for roofing structural verification to ensure safety and stability of the installation. Here we're calculating the string quantity and voltage for the rooftop solar PV system in our factory EPC proposal. Starting with the number of strings, we divide the total number of modules, 1998, by the number of modules per string, which is 18, resulting in 111 strings. For the voltage at maximum power point, or VMP, we multiply the 18 modules by the VMP of a single module, 42.57 volts, giving us 766.26 volts at standard test conditions. However, considering operating conditions at 50 degrees Celsius, the voltage is approximately 689 volts. Next, the open circuit voltage, VOC, is calculated by multiplying 18 modules by the VOC of each module, 50.26 volts, totaling 904.68 volts. This value is safely under the inverter's maximum input voltage of 1100 volts and the system's 1500 volt limit, ensuring safe operation. This calculation is crucial to correctly design the string and inverter configuration for the system. Understanding these voltage limits guarantees system safety and efficiency. Here we focus on the calculation of cold VOC and string current design, which are crucial for ensuring the safety and efficiency of the PV system. First, we use the formula VOC at temperature equals the standard test condition VOC multiplied by 1 plus the absolute value of the temperature coefficient times the difference between 25 degrees Celsius and the minimum temperature. Using a conservative minimum temperature of minus 25 degrees and a temperature coefficient of 0.24% per degree Celsius, the cold VOC calculates to 1013.24 volts, which is safely below the 1100 volt inverter limit. Next, we calculate the design current for each string by multiplying the short circuit current at the module level by a factor of 1.25. For this example, 1.25 times 15.98 amps gives us a design current of about 19.98 amps per string. This means the cable, connectors, and any inline fuses must be rated to handle currents above this derated value to ensure safe operation. We confirm that an 18-module string remains valid under this conservative cold case voltage check. However, the final string design must still be cross-checked against the selected inverter's datasheet, specifically its MPPT voltage ranges, and adjusted based on the local minimum temperature data. It's important to note that parallel string fuses are typically not required unless the inverter or input grouping configuration creates a need for series fuse protection. Finally, 4 key checks are highlighted. Verifying polarity before connection, comparing VOC to expected temperature-corrected values, checking the short-circuit current of similar strings under irradiance conditions, and using a megger to test insulation resistance to earth and between conductors. These steps help maintain system reliability and safety. Here we have the calculation for DC cable voltage drop in our rooftop solar PV system. The formula we use is delta V equals 2 times the cable length times current, times resistivity, divided by the conductor cross-sectional area. For our preliminary check, we assume the resistivity at operating temperature to be approximately 0.0225 ohm millimeters squared per meter. Looking at the examples, for a typical 6 millimeters squared string run of 80 meters carrying 15.27 amps, the voltage drop is 9.16 volts, which is about 1.2%. For a longer 10 millimeters squared rooftop run of 150 meters with the same current, the drop increases slightly to 10.31 volts, or 1.35%. Our design intent is to confirm the final cable routes and groupings to keep the DC wiring loss in line with the PVsyst target of 1.5%. It's important to note that all DC cables must be UV rated for 1500 volts DC and protected from sharp edges and water pooling to ensure durability. Additionally, positive and negative conductors should be clearly tagged at both ends and kept separate from AC and communication cables. Lastly, the final DC and AC cable routing will be verified thoroughly against the roof layout and AC run to ensure compliance and efficiency. On this slide, we're focusing on the AC system, specifically its protection and point of connection. Key components include inverter current management, integration of ACDB and MWh panels, as well as the LVMDP, which is crucial for system coordination. Protection measures and proper earthing are essential to ensure safety and reliability. Additionally, there's a client evaluation package designed to review these elements comprehensively. This section is part of the overall system analysis, numbered as slide 28 out of 103. Here, we have the single-line diagram for the tender basis and point of connection logic for the rooftop solar PV system proposed for the factory. The system features 7 150 kW AC inverters feeding into the outdoor solar ACDB. From there, power flows through the ACDB and main distribution board, or MDB, which are designed with robust 2,500 amp busbars and ACBs, along with metering, current transformers, surge protection devices, and protection relays. The key interconnection point is to the existing 6,300 amp, 400 volt low voltage main distribution panel. It's important to note that final details like cable sizing, breaker duties, protection settings, and shutdown windows will be carefully validated during detailed engineering to ensure reliability and safety. Additionally, an extra MDB panel is included to address any potential gaps at the point of connection, ensuring seamless integration of the solar system into the factory's electrical infrastructure. Here we focus on calculating the inverter and ACDB current for the rooftop solar PV system designed for the factory EPC proposal. The key current formula is I equals power divided by the square root of 3 times voltage times power factor. For each inverter rated at 150,000 watts, using 400 volts and a power factor of 0.94, the current calculates to 230 amps. To ensure reliability and coordination, a 350 amp MCCB is specified, providing a safety margin. Now, looking at the entire plant with a total capacity of 1,050,000 watts, we apply the same formula. This results in a total current of 1,613 amps. Hence, a 2,500 amp AC circuit breaker or busbar is selected, again offering sufficient margin. The table highlights the equipment and their ratings. The inverter feeder MCCB for isolation and protection at 350 amps, the main ACDB or MDB ACB at 2,500 amps with LSIG for switching and selective protection, and protection relays for grid compliance and anti-islanding. Finally, it's important that all low-voltage switchgear installations are door-closed, properly labeled, and ready for lockout-tagout procedures to ensure safety during maintenance. Here we have the calculation for AC cable voltage drop and loss check in the rooftop solar PV system for the factory EPC proposal. Starting with the voltage drop formula, delta V equals square root of 3 multiplied by current, multiplied by the sum of resistance times the power factor cosine plus reactance times the power factor sine, multiplied by the cable length, divided by the number of cable runs. Using a current of 1,613 amperes, a cable length of 178 meters, 5 cable runs, and a resistance of approximately 0.145 ohms per kilometer for our 300 aluminum conductor, we get a preliminary voltage drop of about 13.6 volts, which corresponds to 3.4%. Next is the power loss formula, which estimates the loss as 3 times the square of the current divided by the number of runs, times the total phase resistance, times the number of runs. The conservative preliminary full output loss is approximately 40.4 kilowatts. It's important to note that the final routing and cable schedule must align with the PVsyst AC ohmic loss target to ensure efficiency. Additional considerations include measuring the actual AC route length after tray routing and proof of concept location confirmation. The final cable sizing must account for cable grouping, derating factors, tray covers, and the ambient roof temperature. Also, the final design of the AC cable must meet fault withstand requirements, voltage drop limits, and protective device disconnection times to ensure safety and reliability. Finally, outdoor inverter and AC distribution box stations need clear access, cable tray support, proper drainage, and physical protection to maintain system integrity and ease of maintenance. Here, we're looking at the protection philosophy for the ACDB, MDB, and point of connection in our rooftop solar PV system for the factory EPC proposal. The key functions include voltage relays like 27 and 59, which protect by tripping the PV during undervoltage or overvoltage conditions. Frequency relays 81U and 81O are critical to prevent islanding and ensure the grid operates compliantly. We also have a 2,500 ampere air circuit breaker at the ACDB or MDB to provide selective feeder protection and safe isolation. Surge protection is handled by Type 2 SPDs to reduce equipment damage, while the ESB and RSD provide emergency shutdown capabilities to meet safety requirements and AHJ compliance. The protection approach follows a clear sequence. First, we measure using high-accuracy meters and current transformers. Then protect with ACBs or MCCBs combined with relays. Control via emergency and rapid shutdown systems. And finally verify through trip tests and site acceptance testing. This layered strategy ensures a complete and reliable protection system for safe solar integration. On this slide, we focus on the critical aspects of earthing, equipotential bonding, and the lightning protection system interface specifically for the rooftop solar PV installation at the factory. First, you'll notice the key components involved, such as PV frames with mounting structures, walkways, inverters and distribution boards, earth pits with test boxes, and the existing lightning protection system interface. The table here outlines essential requirements. Continuity is crucial. This means that all metallic structures must be properly bonded and documented as built to ensure safety and functionality. We also must test earth resistance for each earth pit and the overall system, making sure they meet the approved design targets or authority having jurisdiction standards. Surge protection device performance is another vital point. The SPD earth path needs to be short and well bonded, coordinating effectively with the AC and DC protection systems to manage any surges. Lastly, the lightning protection system itself must be reviewed to confirm that the PV installation does not compromise its existing effectiveness. These checks collectively ensure a safe, compliant, and reliable solar power installation integrated with the factory's electrical and protective infrastructure. Here, we focus on monitoring, control, cybersecurity, and CCTV systems. The key components include the data logger and edge gateway, which collect and process data locally. Firewalls are essential for protecting the network from cyber threats, ensuring secure communication. PPC, or Power Protection and Control, manages electrical safety and efficiency. We also integrate weather stations and CCTV systems to provide comprehensive environmental monitoring and security coverage. All these elements work together seamlessly in our client evaluation package, offering robust and reliable system oversight. Here, we are focusing on the monitoring architecture requirements for the rooftop solar PV system in the factory EPC proposal. The core idea is that device data flows from various sources, like inverters, meters, weather sensors, and the PPC, to the manufacturer's data logger or local SCADA system first. It's important to note that no field device connects directly to the monitoring tool's edge gateway, maintaining a layer of separation for security and control. The gateway then securely exchanges data with the approved monitoring platform using VPN or MQTTs over mutual TLS, ensuring encrypted communication. Also, any manufacturer cloud services for logging equipment are not allowed unless formally approved, which keeps data handling tightly controlled. Finally, the zero injection or PPC controller stays logically separate from the monitoring gateway, preserving clear boundaries within the system. Here we have the minimum coverage requirements for the monitoring signal list in our rooftop solar PV system proposal. Starting with the inverters, it's essential to track DC and AC voltage and current, power metrics like kilowatts and reactive power, frequency, power factor, temperature, and any alarms or state changes. Moving to the AC distribution boards and point of connection, we monitor voltage, current, power, energy import and export, breaker and surge protection device status, as well as relay trips. The weather station provides critical environmental data, such as plane of array irradiance, ambient and module temperatures, and wind conditions. For the plant power controller and zero export functionality, we track export power, curtailment commands, set points, and controller health along with communication quality. Lastly, cybersecurity and CCTV monitoring cover firewall and VPN status, device availability, IP mapping, and camera and recording system statuses. It's crucial that all monitoring cabinet components are properly arranged, clearly labeled, and backed up to ensure reliable, comprehensive system supervision. Here we focus on cybersecurity and monitoring backup controls for rooftop solar PV in a factory EPC proposal. A critical formula for sizing the UPS is shown. UPS VA must be greater than or equal to the sum of the load power times autonomy hours, divided by the power factor and efficiency. For example, with a 250 watt essential load, 1 hour of autonomy, a power factor of 0.8, and efficiency of 0.9, we calculate about 347 VA, but select at least a 1 kVA UPS to provide a safe margin. On the cybersecurity side, several key controls ensure secure and reliable operation. First, the SBS OT network should be isolated from the internet except through the main firewall or router. Firewall rules are restrictive, permitting only the minimum necessary hosts, ports, and protocols for data exchange. Default passwords are removed, and used ports disabled, and IP mapping and password handovers are tightly controlled. Secure communication is maintained via VPN or MQTTs using mutual TLS authentication. Access to the manufacturer's cloud is blocked unless explicitly approved. Lastly, monitoring the UPS and 24V DC power supplies prevents unnecessary data loss and supports clean system shutdown and restart. Summarizing these strategies, we segment the network using VLANs for OT, gateway, and cameras, apply strict port filtering on the firewall, encrypt communication with VPN or MQTTs over MTLS, and carefully manage handover of IP maps, rules, and passwords. These steps collectively build a strong defense and reliable backup system for the solar PV installation. Here we focus on the CCTV integration designed for asset and safety surveillance within the rooftop solar PV project. The key element is the use of 4 MP outdoor cameras strategically placed at the inverter station and other critical access points. These cameras are IP67 rated, which means they're built to withstand outdoor conditions, ensuring reliable day and night monitoring. The system is supported by a robust network setup using post switches and a segregated camera network, which enhances security and performance. Locations are carefully chosen to cover the inverter station, rooftop access, material storage, and other approved critical zones, providing comprehensive surveillance. Cybersecurity is a top priority here. Unique credentials and segmented LAN or VLAN configurations protect against unauthorized access, while controlled remote viewing allows secure monitoring. Additionally, our plan includes NVR and storage solutions, so the cameras are fully operational, not just installed, allowing for effective event review and incident management. Importantly, the camera placements respect privacy. Final views will exclude sensitive areas and require client IT and security approval, reinforcing our commitment to responsible, secure surveillance that supports both safety and asset protection. Now let's focus on rooftop access, structural integrity, health, safety, and environmental readiness, as well as operations and maintenance preparedness. Ensuring safe rooftop construction and long-term maintainability is a critical part of any photovoltaic system. We also provide a comprehensive client evaluation package, which helps to verify all these elements are in place and ready. This ensures that the system not only performs well initially, but remains reliable and safe over its entire lifespan. When working at height, especially on rooftops, safety is absolutely critical. Any task performed above 1.5 meters requires specific work at height controls and a detailed method statement tailored to the site or job. Fragile roofs and skylights are particularly dangerous. They pose fatal risks, so walking outside designated safe zones is strictly prohibited. We always prioritize engineering controls first, such as installing anchors, lifelines, skylight protection, and guardrails or hard barriers to provide secure environments. It's important to remember that warning lines serve only as organizational measures and cannot replace these permanent engineering protections. Our fall protection plan comprehensively addresses safety both before and after these engineering controls are in place. On this slide, we focus on the essential rooftop safety measures for the solar PV installation in the factory EPC proposal. Starting with the walkway and access routes, we have a preliminary quantity of 674 meters, designed so that every module is easily accessible for operation and maintenance, ensuring the path remains clear of cables and equipment. Next, the lifelines and anchors, also at 674 meters, must be certified, clearly marked with their capacity, and thoroughly inspected before use to guarantee worker safety. Moving on to the hard barricades or guardrails, approximately 500 meters are planned, featuring a top rail between 1,000 and 1,100 millimeters in height, along with a mid-rail or mesh, and toe boards where necessary to prevent falls. Skylight covers cover about 374 square meters and are designed to withstand a 1,200 joule impact, fixed securely with gratings and accompanied by local danger signage. A key part of the safety approach is the fall protection procedure, particularly around skylight covers and warning lines, which we adhere to strictly. An important calculation shown here is the walkway density, which is the walkway length divided by the total photovoltaic area. With 674 meters of walkway over 5,397 square meters of PV area, this yields a density of 0.125 meters per square meter of collector area. This ratio helps validate the final layout, ensuring all modules are reachable safely and efficiently during maintenance. On this slide, we're focusing on the O&M and cleaning strategy for the rooftop solar PV system as part of our factory EPC proposal. The key aspect here is maintaining safe cleaning, thermal inspection, and access routes to ensure ongoing system reliability. Daily operations include remote monitoring that tracks PV performance, weather conditions, and any abnormal alarms, allowing us to take corrective actions promptly. Then, on a quarterly basis, we perform preventive maintenance checks covering all critical components such as modules, mounting systems, inverters, and balance of system equipment, as well as walkways, lifelines, skylight covers, ladders, and cable trays. Cleaning is scheduled quarterly and increases during high soiling months to keep the modules operating efficiently. The cleaning system is well equipped with water boosters, hose reels, roof taps, and quick couplers for ease of use. Additionally, we conduct thermography and 4-curve sampling to support integrity testing and conduct annual or biannual maintenance to ensure long-term performance. Finally, after project completion, we hold reviews at 30, 60, and 90 days to track production, availability, alarms, performance ratio, and address any open punch list items. This comprehensive approach ensures the system operates at peak performance safely and efficiently. Here we have the BOQ and commercial summary. It's important to note that both the proposal and the Excel BOQ workbook use the same quantities, formulas, and totals, ensuring consistency and accuracy throughout. This alignment is critical for smooth client evaluation and transparency in our financials. The client evaluation package is comprehensive, reflecting all the key components they need to assess. This consistency helps build trust and allows for a clear comparison during the review process. On this slide, we have the BOQ summary aligned with the Excel BOQ for the rooftop solar PV factory EPC proposal. The total price excluding VAT stands at approximately 16.5 billion rupiah, with VAT adding around 1.8 billion rupiah. This brings the total price including VAT to over 18.3 billion rupiah. The price per watt peak excluding VAT is about 12,713 IDR, and including VAT, it comes to 14,111 IDR per watt peak. These commercial values come directly from the Excel sheets BOQ_final and pricing_assumptions. Importantly, the original BOQ structure has been preserved, and any additional completion items are clearly marked in red font as added rows. The final contract price will ultimately be confirmed once detailed engineering, vendor quotations, and the scope freeze have been finalized. Looking at the cost breakdown by category before VAT, the largest portion goes to equipment at roughly 9.37 billion rupiah. This is followed by electrical and cabling costs at just over 3.1 billion rupiah, civil and mechanical at 1.36 billion rupiah, EPCM, TNC, and HSE at 1.88 billion rupiah, miscellaneous costs close to 580 million rupiah, and spares at around 213 million rupiah. This detailed breakdown gives a clear view of how the total project cost is distributed across different aspects of the EPC scope. On this slide, we're focusing on the BOQ additional scope principle, specifically related to the rooftop solar PV for the factory EPC proposal. The key point here is that several added items are critical for ensuring a complete and fully functional system. For example, items like the monitoring logger, edge gateway, firewall, and UPS are essential to establish a secure monitoring architecture with backup and proper handover. Similarly, components such as the solar MDB, POC panel, and power quality monitors are necessary for safe point-of-connection integration and export control. We've also included security and safety elements like CCTV storage and fire extinguishers to ensure these functions are operational. Additionally, physical protections such as cable tray covers and drainage tackle potential site condition variations that could otherwise compromise equipment. Importantly, spare parts and PP are added to support maintainability and system reliability after completion. These aren't just cosmetic additions. The red rows in the table highlight the scope gaps we're closing so the system can be built, tested, and handed over safely and comprehensively. All these added items are thoroughly documented in the added_items_log Excel sheet and incorporated into various project management sections like BOQ, WMS, and commissioning to minimize variation risks and reinforce complete EPC accountability. This approach ensures the project is delivered securely and reliably from start to finish. Now, moving on to component visualization and installation details. This involves a detailed look at each piece of equipment, showing how it fits into the overall construction sequence. By visualizing equipment step by step, we provide a clear understanding of the installation process. This is presented as part of the client evaluation package, ensuring that our clients have all the necessary information to review and approve the sequence before work begins, which is crucial for smooth project execution. Here we have a comprehensive component matrix providing a complete system view of the rooftop solar PV setup proposed for the factory EPC project. The key components include nearly 2,000 PV modules, each rated at 650 watts, carefully installed with attention to clamp zones, torque specifications, and damage prevention. Moving on, the DC strings consist of 111 strings with 18 modules each, where we ensure correct polarity and proper labeling for safety and efficiency. The system includes 7 inverters, each with a capacity of 150 kilowatts AC, requiring appropriate clearance and segregation between AC and DC parts to maintain safety and performance. The AC distribution boards are designed for a 2,500 amp bus bar, with rigorous testing like factory acceptance tests and relay trip verifications to ensure reliability. For monitoring and control, we integrate loggers, gateways, firewalls, and sensors, supported by CCTV to provide thorough oversight, with cybersecurity measures and platform acceptance tests in place. Lastly, the safety system incorporates lifelines, walkways, guardrails, and skylight covers, all certified and inspected regularly with a rescue plan and preventive maintenance program. Altogether, these components are meticulously integrated with the roof, electrical, monitoring, and safety infrastructure to deliver a robust and secure solar power installation. Let's walk through the step-by-step process for PV module installation, focusing on the key components and installation details. First, when we receive the modules, it's essential to check the packaging, verify serial numbers against the flash list, and inspect for any transport damage. Always handle the modules carefully during positioning, ensuring two-person handling and never stepping on the modules to prevent damage. Next, the modules are clamped securely at approved clamp zones using calibrated torque to maintain structural integrity. After clamping, we map the modules by recording their serial numbers against the layout and string map, which is crucial for tracking and future maintenance. The final step involves a thorough inspection, including visual checks, verifying torque settings, grounding, and connectors. Throughout the installation sequence, we integrate quality assurance and control measures alongside health, safety, and environmental protocols. This ensures no broken glass, frame deformation, delamination, wrong orientation, or loose clamps, while documenting all records meticulously and following approved safety procedures. This comprehensive approach guarantees a reliable and safe PV module installation every time. Let's walk through the step-by-step process for installing the MMS or microrail system on the rooftop solar PV setup. First, we start with the survey, where we confirm the purlin lines and assess the condition of the roof. This step is crucial to ensure a proper foundation for the installation. Next, the pull-out test is conducted to check representative fixing points and verify their strength. Moving on to the rail installation, we install the approved microrail or roof clamp securely. After that, Torque is applied to the bolts and fasteners, and torque marks are made to confirm correct tightening. Then we bond all the rails together, making sure to verify electrical continuity. It's important to note that no MMS work can begin until we have structural sign-off and an approved fixing method. Installers must take care to avoid damage to the roof sheets and confirm that waterproofing and sealants remain intact after installation. Finally, all metallic rails, walkways, and support frames become part of the equipotential bonding network to ensure safety. Remember, roof installation requires engineered access before any production work can start to maintain safety and quality standards. Let's walk through the DC string cabling and labeling process step by step for our rooftop solar PV system. First, we lay the UV 1500 VDC cable in a protected route to ensure durability and safety. Next, it's important to keep DC cables separated from AC and communication lines to avoid interference. Then, when terminating the cables, we use connectors from the same family to maintain consistency and reliability. After that, we label each string by tagging both ends with the string ID and polarity, which is crucial for easy identification and troubleshooting. Finally, before making any connections, we thoroughly test polarity, open circuit voltage, short circuit current, and insulation resistance. This careful approach aligns with our DC string architecture, which follows the single line diagram and the inverter's MPPT grouping. As you can see in the table, we have a total of 111 strings distributed across 7 inverters, supporting nearly 2,000 modules and delivering a capacity of almost 1.3 megawatts peak. This structured method ensures a safe, efficient, and well-organized solar installation. Here, we focus on the installation details of the inverter station, both physical and electrical aspects. The inverter racks or plinths must be installed on a properly approved foundation that includes drainage and anti-corrosion measures to ensure durability and safety. It's crucial to maintain the manufacturer's recommended clearances for heat dissipation and easy access during servicing. For safety, we provide a lockable fence or gate, bollards, warning signs, and fire extinguishers near the electrical equipment. Additionally, cables are carefully segregated, AC, DC, and communication wires are separated, with cable trays covered and drip loops installed where necessary to protect against moisture. Finally, all terminations are torque marked and undergo thermographic checks during commissioning to verify their integrity. Let's walk through the step-by-step process for ACDB, MDB, and POC panel installation, focusing on the key components and installation details. First, we start with the FAT, which includes a thorough panel FAT and document review to ensure everything is in order. Next, we prepare the installation site by positioning the plinth or rack and the enclosure correctly. Then, it's crucial to connect the protective earth and bonding first for safety. After that, we proceed with termination, including glands, lugs, heat shrink applications, and proper torquing. Finally, we conduct comprehensive testing, such as insulation resistance, current transformers, relay checks, and breaker functionality. The critical components vary by panel type. The ACDB includes 7 inverter feeders, a 2500A ACB, MFM, CTs, SPDs, and protection relays. The MDB and POC panels feature a 2500A ACB, CTs for metering, relays, SPDs, and the LVMDP tie-in interface, while the existing LVMDP requires an approved shutdown, busbar and tapping verification, and a protection and selectivity review. Throughout the process, panel workmanship, labeling, and lockout/tagout readiness are essential quality points visible to the client, underscoring our commitment to safety and reliability. First, we start by finalizing the shutdown date in coordination with the client's operations, but only after completing the LVMDP survey and getting the method statement approved. Then, we prepare a detailed switching program that includes the lockout-tagout register, defining the energized work boundary, and setting up an emergency response plan. To keep disruptions minimal, all offline components are installed prior to the actual shutdown. During the shutdown itself, we carefully follow a sequence. Isolate the system, apply lock and tag procedures, confirm the system is de-energized, perform the installation and tie-ins, check all torque connections, and conduct insulation resistance and continuity tests. Finally, once the system is re-energized, we verify metering accuracy, confirm phase sequence, check relay status, ensure breaker operation, and monitor all relevant points to ensure everything is functioning safely and correctly. This systematic approach ensures a smooth and controlled integration process. Here we have the key component and installation details for the rooftop solar PV system proposal. The monitoring system uses a logger or SCADA, which we install inside an IP-rated cabinet to protect it. All data from inverters, meters, and sensors is first terminated to this logger. The edge gateway and firewall are installed separately from field devices to maintain security, and only approved VPN or MQTT secure data paths are enabled. For the PPC or zero export functionality, we wire the proof of concept meter and current transformer interfaces along with inverter control setpoints, then conduct tests to ensure proper curtailment response. The weather station sensors, including plane of array, global horizontal irradiance, temperature, and wind, are mounted away from shade and positioned for easy cleaning and calibration. CCTV components like cameras, post-switch, and recording equipment are installed with client-approved access for monitoring. Finally, the entire monitoring cabinet is clearly labeled, securely enclosed, and supported by uninterrupted power supply with UPS and 24-volt DC backup. These additions are essential for delivering a complete, reliable system. Let's go through the earthing and bonding installation steps for the rooftop solar PV system on the factory EPC proposal. First, we start by installing earth pits and inspection boxes, which are fundamental to establishing a reliable grounding network. Next, we bond all the PV frames, rails, trays, and fences to ensure they are at the same potential, preventing any dangerous voltage differences. Then, we move on to bonding critical electrical components such as inverters, ACDB, MDB, and the cabinets to secure the entire electrical system. Lightning protection systems and surge protective device earth connections must be coordinated carefully to maintain system integrity during transient events. Finally, we conduct thorough continuity and resistance tests to verify the earthing system's effectiveness. The protective conductor size is determined using the formula S equals I times the square root of T divided by K, with the size finalized after proof of concept short circuit levels and disconnection times are confirmed. Remember, earthing is not just about running cables. It's about creating a verified equipotential network that ensures electrical safety and surge protection. The as-built earth map should clearly document pits, test links, bonding paths, and lightning protection system interface points. Before energizing the system, we confirm the quality of panel bonding and cable termination to guarantee safe and reliable operation. Here we focus on the critical aspects of fire safety signage and accessory installation for the rooftop solar PV system. First, fire extinguishers like a PAR CO2 or DCP must be mounted near the inverter station or electrical room with proper signage, ensuring they are visible, easily accessible, and included in preventive maintenance. Next, all PV warning labels should be placed on DC and AC panels, string tags, cable tags, and roof access points. These labels need to be durable and displayed in the local language where required to ensure clarity. Emergency stop buttons or rapid shutdown devices must be installed according to authority having jurisdiction or design specs, and their trip and reset functions must be fully tested. Cable tray accessories such as covers, bends, tees, clamps, and supports are important to avoid any sharp edges or cable sagging, and metallic parts need to be properly bonded for safety. Finally, physical protections like bollards, fencing, lockable gates, and adequate drainage are essential to protect equipment from physical impact and water pooling. These additions are crucial for completing a safe and compliant system. Here we have the work method statement, which is essentially a detailed step-by-step guide to how the construction will be executed. It covers all the important controls and records to make sure everything is done correctly and safely. This document is also a crucial part of the client evaluation package, helping them understand and approve the planned methods before work begins. Keeping this statement clear and thorough is key to smooth project execution. Here's an overview of the work method statement execution flow for the rooftop solar PV project. The process begins with the prepare phase, where we handle engineering details, submittals, HSE plans, and all necessary permits. Next, we focus on making the site safe, installing access points, lifelines, guardrails, and walkways to protect everyone involved. After safety is ensured, we move into building the DC side of the system, including mounting modules, creating strings, and conducting DC testing. Following that, we build the AC side, which involves installing inverters, AC distribution boards, points of connection, and proper earthing. Finally, the commissioning phase covers all levels of testing, handover procedures, and project management. The key element here is the WMS sheet, which details 20 method steps and links each to HSE controls, quality assurance, and the bill of quantities. Every activity must meet strict prerequisites like approved drawings, material approvals, risk assessments, trained workers, calibrated tools, and permits to work. This method statement is designed to minimize client risk by ensuring safe construction, progressive testing, and avoiding surprises at the point of connection or handover. Here we have the first stage of the work method statement, focusing on mobilization, site setup, and roof access for the rooftop solar PV installation. The key steps begin with the engineering freeze, where we confirm the layout, single-line diagrams, cable routes, handover methods, HSE plans, and the shutdown window. This step is documented through IFC drawing registers and design review minutes. Next is the site induction, which includes toolbox talks, permit to work processes, and emergency briefings, all recorded in induction attendance logs and PTW registers. Then we establish temporary facilities such as laydown and storage areas, waste management, temporary power, and clear material routes, tracked via a site setup checklist. Finally, the roof access inspection ensures ladders, roof sheets, skylights, weather conditions, edges, and existing services are safe to proceed, with permits and photo reports as records. It's crucial to remember that no roof work can begin without an approved working at height or WAH plan, a weather check, and a valid permit to work. Before starting any rooftop solar PV work, it's crucial that we first complete all necessary engineering controls to ensure safety. The key steps begin with installing lifelines and anchor points, which must be certified systems with clearly marked load capacities and be inspected before use. Next, skylight covers or gratings need to be securely fixed to prevent accidental displacement, built to withstand impacts of 1200 joules and marked with danger signs. Following that, guardrails or hard barriers must be installed, with specifications such as top rails between 1,000 and 1,100 millimeters high, along with mid-rails or mesh and tow boards if needed. Finally, designated walkways or access routes should be set up. These need to be free from cables or equipment, properly bonded, and inspected to guarantee safety. It's important to remember that engineering controls like these are completed before any general rooftop PV construction takes place. Also, warning lines by themselves are not considered permanent safety measures. They serve as early-stage organizational controls only. And absolutely no walking is allowed on fragile roof sections outside the approved access pathways. This careful approach is vital to maintaining safety during the entire installation process. On this slide, we're focusing on the key steps in WMS Stage 3, which covers the mechanical mounting structure, or MMS, the solar modules, and the DC cabling. First, we start with the pull-out test to verify the fixing strength of the MMS. This is crucial because the mounting system must be securely attached to the roof to ensure stability and safety. Once the MMS fixing and roof condition are confirmed, we proceed to install the microrails and correctly torque them to specification. Next, the modules are installed using a careful two-person method to avoid any damage, with strict rules like no stepping on modules to maintain quality. We then clamp the modules in place and create a serial map for proper electrical configuration. After that, we handle the DC cabling by routing, labeling, and terminating all cables accurately to maintain clear connections. Before finalizing, we conduct several DC tests to check for polarity, open circuit voltage, short circuit current, and insulation resistance. These string tests are essential because they verify the electrical integrity of each string before connecting to the inverter, and all results are documented in the as-built string map. Ultimately, the quality of your MMS and module installation depends on following a disciplined layout process and conducting progressive testing throughout. This approach ensures reliability and ease of commissioning later on. Here we outline the key steps involved in the WMS Stage 4 for the inverter station, ACDB, MDB, and point of connection. First, the civil plinth needs to be constructed with proper drainage and bollards for protection. Next, we mount the inverters, ACDB, and MDB carefully on this foundation. Then, termination of AC cables, including lugs and glands, is performed to ensure secure electrical connections. A critical safety procedure is the lockout-tagout process to shut down the system and verify it is completely de-energized before any work proceeds. Following this, the tie-in to the LVMDP is conducted, but only during an approved client shutdown and under strict LOTO control to maintain safety. It's important to confirm that all panels are earthed before termination, and that meters and labels are accurately verified with doors closed to prevent hazards. The point of connection work also includes checking CT orientation, phase sequence, protection settings, and comparing meter readings after energization to ensure system accuracy. Throughout the installation, the AC equipment must be installed with safety, maintainability, and protection from weather and impact firmly in mind, so the system remains reliable and secure over time. At WMS Stage 5, we focus on monitoring, commissioning, and handover for the rooftop solar PV project. First, during the monitoring phase, we install key equipment like loggers, gateways, firewalls, PPC systems, sensors, cameras, and NVR units, ensuring a secure data path is configured. This allows us to generate detailed point-to-point reports, IP maps, and firewall rules. Next, we conduct comprehensive static testing, including infrared, polarity, earth, current transformer, relay, and panel testing, all completed before energization to guarantee system integrity. The results are documented in CXL-2B reports. During startup and system acceptance testing, we perform sequential energization and inverter startup, followed by protection settings, zero export, and monitoring tests, producing CXL-3 and CXL-4 reports. Finally, integrity checks and handover involve performance runs, thermography scans for sampling, and comprehensive O&M training for the client. The full handover package includes all as-built drawings, warranties, spare parts lists, training records, test reports, and a preventive maintenance schedule. This thorough monitoring and commissioning process demonstrates our strong client-facing execution capability. It ensures the system is fully operational, reliable, and ready for long-term maintenance. On this slide, we're focusing on the inspection and test plan, often referred to as the ITP, and its role in quality assurance and quality control. The ITP outlines critical hold points and witness points, which are specific stages in the process where inspections or tests must occur before proceeding. These points help ensure that the work meets the required standards before moving forward. Additionally, maintaining accurate records and clearly defined acceptance criteria is essential for verifying compliance and quality. Finally, the client evaluation package compiles all this information for review, providing transparency and confidence in the project's quality. This comprehensive approach helps maintain high standards throughout the project lifecycle. Here we have the ITP model illustrating quality gates across the project lifecycle for our rooftop solar PV factory EPC proposal. The process is divided into 5 key stages. First is FAT, where factory records and routine tests are conducted. Next, MIR involves material receiving inspection to ensure everything meets standards. Then during the install phase, we perform QA/QC checks and record torque data to confirm proper assembly. Following that is the static stage, which includes essential electrical tests like IR, continuity, earth, CT, and relay verification. Finally, SAT focuses on functional and performance verification to ensure the system meets all operational requirements. These quality gates are critical checkpoints that help maintain high standards throughout the project. To manage this, we categorize quality status into hold points, where work cannot proceed without client or EPC release. Witness points, which allow work to continue after notification if no hold is issued. Review points, for document and result reviews kept in the handover dossier. And NCR or punch items that track nonconformities requiring corrective actions with responsible ownership and proof of closure. This structured approach ensures transparency and accountability at every step. Here we have the main equipment quality gate for the factory acceptance test, or FAT, in our rooftop solar PV proposal. The table highlights key equipment and their respective FAT or review activities alongside acceptance criteria. For the PV modules, we verify certificates, flash lists, serial traceability, and packaging. Approval is based on a 650 watt peak standard and adherence to IEC records. Inverters undergo routine testing, including firmware checks, communications, and warranty validation. Only models approved for 150 kilowatts AC and those that pass FAT are accepted. Next, the ACDB and MDB components are checked for busbar quality, circuit breakers, relays, wiring, and other electrical elements. Acceptance requires a 2,500 ampere basis with confirmed mechanical and electrical operation. Finally, monitoring and power plant controllers must have validated loggers, gateways, firewalls, licenses, and tag lists, ensuring all mandatory tag families and secure architecture are in place. Approving these FAT processes early on significantly minimizes site rework, client rejection, and commissioning delays, ensuring a smoother project delivery. Here, we focus on the installation quality assurance and quality control, or QA/QC, for the rooftop solar PV system proposed for the factory. The key activities cover several critical areas. First, rooftop safety controls include checking lifelines, guardrails, walkways, skylight covers, ladders, and verifying certificates, all documented through work-at-height inspections and third-party certificates. Next, for the MMS and module installation, we inspect fixing, alignment, clamp zones, torque, serial mapping, and roof conditions, with records kept in torque sheets and module checklists. The DC and AC cable routing ensures proper segregation. Tray covers, bend radius, glands, lugs, and labels, recorded via cable installation checklists. Lastly, earthing and bonding are verified through inspection of pits, test links, frames, rails, trays, panels, and lightning protection system interfaces, supported by bonding maps and continuity checklists. This phase confirms that the system, although not energized yet, has passed all mechanical, safety, and quality controls, ensuring a solid installation foundation before commissioning. This is critical to maintain safety and performance standards moving forward. Here we have the CXL2B static test ITP for the rooftop solar PV system proposed for the factory. This section focuses on the quality assurance and quality control procedures to ensure system reliability. The key tests include checking the PV string polarity and open circuit voltage, where we must confirm there is no reversed polarity and the voltage falls within the expected temperature-corrected range. Next, we sample the string current under proper irradiance and compare it across similar strings to identify any abnormalities that need correction. We also perform insulation resistance tests using a megger, verifying that the DC and AC insulation meet the approved voltage and resistance thresholds. Additionally, earth resistance and continuity tests confirm proper grounding according to design and authority having jurisdiction targets. Finally, the protection static tests cover current transformer ratios and polarity, relay wiring, and breaker trip functions to ensure correct trip paths and alarm events. This thorough testing is crucial for a safe and efficient solar PV installation. Here we have the key stages involved in the CXL3 and CXL4 IDP processes for startup and SAT, specifically for the rooftop solar PV EPC proposal. First, during the CXL3 startup phase, we focus on pre-energization readiness, sequential switching, and inverter startup. The goal here is to ensure there are no critical punch items and no abnormal trips or alarms, while maintaining voltage and frequency balance. Moving to CXL4 SAT protection, we test critical protection functions like relay tripping and alarms to verify correct operation, event logging, and reset capability. For CXL4 SAT PPC, we simulate power export and curtailment, making sure export levels stay within the approved tolerance. Finally, in CXL4 SAT monitoring, we validate the remote platform's security and visibility by checking alarms, trends, reports, and cybersecurity measures. The step-by-step sequence moves from readiness, with CXL2A complete, to energizing equipment, switching per program, starting inverters one by one, testing the trip functions including protection and emergency stop, and finally monitoring PPC performance and platform functionality through SAT. Each step is critical to ensure a smooth and safe system startup and acceptance testing. At the CXL5 level, we focus on integrity and performance verification. This includes monitoring continuous operation, checking for alarms, and analyzing the performance ratio trends to ensure there are no unresolved critical alarms and that production meets expectations. Additionally, thermography and 4-curve sampling help confirm there's no critical hotspot or unexplained underperformance. Moving to CXL6, handover is critical, where we provide a complete dossier including as-built drawings, operation and maintenance manuals, warranties, spares, and test reports, all accepted by the client. After project completion, we conduct 30, 60, and 90-day performance reviews and activate preventive maintenance schedules to track and close any open issues. This transition from construction to reliable operation is essential for the long-term success of the rooftop solar PV system. On this slide, we focus on the NCR, punch list, and document control process within our QA/QC framework for the rooftop solar PV EPC proposal. The process begins with detecting any issues through thorough inspections and tests. Once identified, these issues are classified into 3 categories: critical, major, or minor. We then assign responsibility by designating an owner, setting a due date, and gathering necessary evidence to track progress. Correction involves repairing the problem, retesting, and uploading all related records. Finally, the issue is closed after receiving acceptance from the client or EPC. Additionally, our documentation is organized into several key records: daily QA/QC reports capturing progress, resources, weather, and photos, detailed inspection records including checklists and measurements, a punch/NCR tracker that logs issues with their risk levels and status, and a comprehensive handover dossier containing as-built drawings, test results, manuals, and maintenance schedules. This systematic approach ensures quality control and transparency throughout the project lifecycle. On this slide, we're focusing on the risk register and risk assessment, which are crucial tools for managing project risks effectively. The risk matrix helps us evaluate and prioritize key hazards by assessing their likelihood and potential impact. We then identify appropriate mitigations to reduce these risks, along with residual controls that remain after those measures are implemented. Additionally, this information is compiled into the client evaluation package to ensure transparency and informed decision-making. Overall, the emphasis here is on systematically identifying, assessing, and controlling risks to maintain project safety and success. Here we have the risk matrix for rooftop solar PV installation in the factory EPC proposal. The matrix calculates risk by multiplying the probability of an event by its severity, giving us a clear way to prioritize risks. You can see how the risk bands range from low to critical, with scores from 1 up to 25. Scores between 20 and 25 are considered critical, requiring a hold point, method statement, and manager approval before proceeding. High risks, scoring 12 to 19, need detailed control plans and daily supervision. Medium risks, from 6 to 11, are managed with standard controls and ongoing monitoring. Finally, low risks scoring between 1 and 5 require only routine control. This structured approach helps us focus our attention and resources where they're needed most to ensure safety and efficiency throughout the project. Here we focus on the top work at height and dropped object risks that we must carefully manage on the rooftop solar PV installation project. The most critical risk is a fall from edges or skylights, which could lead to fatality or severe injury. To prevent this, we prioritize engineering controls and enforce 100% tie-off, use skylight covers, and prohibit lone working. Another significant hazard is dropped tools or materials that can cause injury or damage below. We control this by using tow boards, tool lanyards, establishing exclusion zones, lifting plans, and maintaining good housekeeping. Additionally, unsafe roof loading poses a risk of structural damage or fall-through, so we conduct structural reviews, control personnel spacing, and designate approved walkways and access routes. Weather exposure is also a key concern, requiring daily weather checks and strict enforcement of stop work rules during wind, rain, or lightning. You'll see that risk reduction is supported by permanent safe access and robust work controls. Meanwhile, residual risk is managed through competent supervision, permit-to-work systems, detailed work-at-height rescue plans, and regular inspections to maintain safety at all times. Here we focus on the electrical, lockout-tagout, and energization risks associated with our rooftop solar PV proposal for the factory. The most critical risks include DC shock or arc hazards from the photovoltaic strings, which can lead to injury, fire, or equipment damage. To control this, we treat all strings as live during daylight hours, use DC isolation methods, insulated tools, and perform polarity, open-circuit voltage, and insulation resistance tests. At the point of connection, low-voltage arc flashes pose a severe risk of fatality and major outages. This is managed by implementing approved shutdown procedures, strict lockout-tagout protocols, proving the circuit is dead before work, enforcing an arc flash boundary and limiting access to authorized personnel only. Incorrect current transformer or relay settings can cause trip failures or nuisance trips. We mitigate this risk by verifying CT ratios and polarity, conducting relay injection tests, and performing secondary acceptance testing on the station auxiliary transformer. Lastly, unexpected export to the grid can lead to non-compliance issues. Controls include using zero export or power plant controller strategies, installing a point of connection meter, carrying out secondary acceptance tests with export simulation, and closely managing set-point controls. Overall, electrical safety is rigorously maintained through disciplined lockout-tagout procedures, comprehensive testing, and ensuring only qualified personnel perform critical tasks. Here we have several key risks associated with rooftop solar PV installations on factories, specifically focusing on structural, waterproofing, and weather-related challenges. First, roof overload or fixing failure can occur if the purlin capacity is unverified or if the wrong fixing method is used. To mitigate this, we conduct a thorough structural assessment, perform pull-out tests, and ensure all fixings are approved with torque records. Next, roof leakage risks arise from penetrations, damaged sheets, or poor sealing. We address this by doing pre- and post-water tests, using approved sealants, documenting with photos, and providing allowances for repairs. Corrosion is another concern, especially in industrial or coastal environments, or when incompatible materials are used. This is managed through careful material selection like hot-dip galvanizing, aluminum, or stainless steel 304. Using isolation washers and scheduling periodic inspections. Finally, weather delays due to rain, wind, or lightning during roof work are mitigated by maintaining a look-ahead schedule, performing daily weather checks, setting stop work thresholds, and securing materials properly. All these risks are effectively controlled through a carefully sequenced process from survey to engineering, testing, installation, inspection, and thorough documentation. This structured approach is key to a successful and safe rooftop solar PV installation. Here we focus on monitoring, cybersecurity, and operations and maintenance risks for the rooftop solar PV project. The risk register lists 5 key risks along with their impacts and mitigation strategies. First, uncontrolled OEM cloud paths can expose data and control systems, so we block any uncontrolled cloud access using approved firewalls, VPNs, and secure MQTT protocols. Next, monitoring outages can cause loss of performance visibility, which we address by implementing backup power supplies, industrial switches, and alerting through point-to-point tests. Sensor drift or dirty pyranometers can lead to incorrect performance ratio analysis, so regular cleaning, calibration, and data reasonableness checks are essential. CCTV and NVR failures reduce security and health safety surveillance, which we mitigate by maintaining storage, power supplies, preventative maintenance, and having spare cameras ready. Lastly, poor O&M access can risk unsafe maintenance or damage to modules, so walkways, lifelines, skylight controls, and annual inspections are put in place. Each of these measures ensures the system's reliability, security, and safety throughout its life cycle. On this slide, we're focusing on the critical aspects of risk governance and HSE key performance indicators for the rooftop solar PV factory EPC proposal. The target total recordable incident rate, or TRIR, is set to be less than 1 per million hours worked, which highlights our commitment to safety. We also aim for a robust HSE anomaly reporting system, targeting at least 1 report per person per month to ensure continuous monitoring and improvement. When it comes to high-risk activities like work at height, we're striving to achieve 100% control implementation to prevent any incidents. Before energization, the goal is to have 0 critical punch list items, reflecting our focus on thorough safety checks and project readiness. Looking at governance mechanisms, daily toolbox talks and permit-to-work reviews cover hazards like weather conditions, lockout-tagout procedures, and rescue controls, ensuring every task is safe before work begins. Weekly risk register reviews keep all open risks updated with responsible owners and mitigation plans. In addition, client witness and hold points are set for high-risk stages to confirm safety and quality standards before proceeding. Finally, lessons learned from near misses, anomalies, and nonconformance reports are actively used to improve and update our methods, reinforcing a culture of continuous safety improvement. On this slide, we focus on LOTO and energization safety, which is critical for preventing accidents during maintenance. Key concepts include defining clear isolation boundaries to ensure that energy sources are properly controlled. The prove-dead method is an essential step where you verify that all energy has been safely disconnected. We also cover the correct switching and restoration sequence to avoid unintended energization. Finally, there's the client evaluation package, which helps assess compliance and understanding of these safety procedures. These elements together create a comprehensive approach to keeping everyone safe. Here we're looking at the lockout-tagout philosophy and how isolation boundaries are established, especially in the context of rooftop solar PV systems for factories. The key point is that LOTO separates different types of electrical hazards, specifically DC hazards from the PV strings, AC interconnection hazards, and any stored or control energy hazards. It's important to understand that PV strings upstream of DC isolation stay live as long as they're illuminated, so they have to be treated as energized under all conditions until officially confirmed safe. Also, any work on the existing low-voltage main distribution panel requires a formal release from client operations and must be handled by authorized electrical personnel only. To ensure safety, every worker applies their personal locks and tags or uses an approved lockbox system, so nobody can accidentally re-energize the system while work is ongoing. Here we have the step-by-step process for lockout-tagout, or LOTO, which is critical for ensuring safety during electrical work. First, we authorize the procedure by securing proper permits to work, reviewing the switching plan, and getting client approval. Then, we identify all energy sources and establish clear boundaries to prevent accidental re-energization. Next is isolation. This means opening breakers or isolators and applying locks to physically prevent power flow. After isolation, we verify by conducting tests, including the live-dead-live test, to confirm the equipment is truly de-energized. Once verified, work can proceed with careful maintenance of boundaries and thorough job briefings. And finally, we restore the system by inspecting the work area, removing locks, and safely re-energizing the equipment. The table here outlines essential documentation to support each step, including switching programs, LOTO registers, verification forms, and restoration records, ensuring accountability and safety throughout the entire process. On this slide, we're focusing on the critical precautions for PV DC isolation, especially under lockout/tagout or LOTO procedures. First, it's important to understand that strings remain live when exposed to sunlight, so you cannot rely solely on disconnecting connectors for safety. Instead, always use the inverter's DC isolator along with an approved procedure. Next, to avoid dangerous DC arcs during load break, never disconnect MC connectors while under load. Follow the proper inverter shutdown and test sequence. To prevent issues like wrong polarity or cross-connection, conduct polarity and open circuit voltage checks before termination, and make sure every string is clearly tagged at both ends. Also, be mindful of stored control energy by isolating monitoring, UPS, and control supplies when working inside control cabinets. The formula here helps verify DC voltage. Multiply the number of modules in series by the module voltage and a temperature factor to get the expected open circuit voltage, or VOC. Your measured VOC should fall within this predicted range before connecting to the inverter. Finally, all DC isolation points must be clearly shown on the as-built single-line diagram and the LOTO diagram to ensure safety and compliance. Here we have the AC/POC isolation and switching sequence, which is crucial for ensuring safety during the installation of the rooftop solar PV system. The isolation boundary is our most critical safety interface because it involves working with the existing energized factory infrastructure. To minimize risks, shutdown work is kept as short and controlled as possible, with thorough preparation done offline before any shutdown occurs. The restore sequence follows a carefully managed process with verification of meters, relays, breakers, and phase sequences to ensure everything is safe and functional. Additionally, lockout-tagout, or LOTO, readiness must be clearly visible on the panel doors, featuring single-line diagram mimics and warning labels. This visibility helps everyone involved recognize the safety status at a glance before proceeding. Here, we focus on emergency response, rescue, and restoration protocols specific to rooftop solar PV installations. Each scenario demands a precise and swift response to ensure safety and minimize damage. For an electrical incident, work must stop immediately, and if it's safe, isolate the source. Emergency calls should be made without delay, and first aid or CPR administered by trained personnel while notifying the relevant parties. In the case of a fall or a suspended worker, we must implement the rescue plan right away to avoid prolonged suspension, with a first aider and clear evacuation routes ready. For fire or smoke at the inverter or panel, an emergency stop or isolation is necessary if it's safe, followed by using the appropriate fire extinguisher and evacuating non-essential personnel. Any unexpected live readings require stopping work, establishing a safety boundary, investigating how to isolate the issue, and revising the method before restarting operations. Finally, for LOTO restoration, it's crucial to ensure all personnel are clear, tools are removed, covers are reinstalled, and authorization is obtained from the client or EPC before re-energizing the system. These steps are vital for maintaining a safe working environment throughout the project. Here we have the testing and commissioning roadmap, which spans from CXL1 to CXL6. This roadmap outlines a progressive verification process that starts with factory tests and continues all the way through to the post-completion performance review. It's important to note that this ensures thorough validation at every stage. Additionally, the client evaluation package is a critical component, providing the necessary documentation and feedback for client assessment. This comprehensive approach guarantees that all systems are functioning optimally before final acceptance. Here we have an overview timeline for the testing and commissioning phases, covering levels CXL1 through CXL6 for the rooftop solar PV project. Starting with CXL1, we focus on factory acceptance tests, which include factory tests and certification to ensure quality from the source. Next, at CXL2A, we perform installation quality assurance and quality control through visual and installation checks. Then in CXL2B, we conduct static tests like insulation resistance, polarity, earth continuity, and relay functionality. Moving on to CXL3, this is the startup phase that involves the first energization and system startup. CXL4 is the site acceptance testing, confirming that the system performs functionally in its actual environment. At CXL5, we evaluate the system's integrity by monitoring performance and continuous operation to verify reliability. Finally, CXL6 covers handover, which is more than just document transfer. It includes training, preventive maintenance activation, and a thorough 30, 60, and 90-day post-completion review. This staged commissioning plan is designed so defects are identified early, preventing issues from progressing to later stages. Each level has clear inputs, methods, acceptance criteria, and witness points, ensuring a rigorous, structured process. Here we have the Factory Acceptance Test, or FAT, which is a crucial step before delivering and installing the rooftop solar PV system. The FAT ensures that all major equipment, like PV modules, inverters, ACDB and MDB panels, and the monitoring system, meet strict quality and performance standards. For PV modules, we check IEC certificates, flash lists, serial traceability, and packaging. Inverters undergo routine testing, firmware and settings verification, and communication checks. The panels are tested for bus bars, circuit breakers, meters, wiring, and mechanical interlocks, while the monitoring system is verified for hardware, software, licenses, and tags. FAT acceptance is mandatory before any equipment is released for delivery or installation, guaranteeing reliability and smooth commissioning. Now, let's review the CXL2A installation check for quality assurance and quality control during the testing and commissioning phase of our rooftop solar PV project for the factory. Starting with Rooftop HSE, we ensure that all safety measures like access points, lifelines, skylight covers, guardrails, walkways, and rescue arrangements are properly in place and approved before any PV work begins. Moving on to the modules, we check the fixing, alignment, torque, clamp zones, serial mapping, and record the roof condition to make sure everything is correctly installed and documented. For DC and AC cabling, we verify the routing, labeling, tray covers, glands, lugs, as well as the separation and bend radius, to avoid any electrical issues. Panels and earthing are thoroughly checked for secure fixing, proper earthing and bonding, clear labeling, lockout-tagout points, and accurate single-line diagram mimic. Finally, the monitoring and CCTV aspects include verifying the cabinet setup, power backup, network segregation, and the correct mounting of cameras and sensors to ensure reliable system oversight. These checks are critical to guarantee both safety and performance before commissioning the solar PV system. Here we have the static test procedures for the DC system of the rooftop solar PV installation. First, we check the polarity by measuring the string's positive and negative terminals before connection, ensuring there's no reversed polarity, which is critical for safety and proper operation. Next is the open circuit voltage, or VOC, where we measure each string's voltage and compare it to the temperature-corrected expected value using this formula. This lets us confirm the VOC is within expected tolerance under current field conditions. Then we measure the short circuit current, or ISC, for representative strings under irradiation to detect any abnormal mismatches that might indicate faults or shading issues. For insulation resistance, we use a megger to test the strings and cables to earth and between conductors, making sure the resistance meets the approved minimum threshold to avoid leakage currents or hazards. Finally, connector and termination tests include visual and pull checks, verifying that connectors are from the same family and show no signs of looseness or cracks. The design current is calculated here as 1.25 times the ISC, which comes to just under 20 amps, and it's important that cable and connector ratings, as well as test equipment, exceed this derated current for reliable and safe operation. Overall, this thorough testing ensures our DC system is correctly installed and ready for commissioning. Here we have the CXL2B static tests focusing on AC, earth, and protection systems, which are crucial parts of the rooftop solar PV installation for the factory EPC proposal. First, for the AC cables, we perform insulation resistance and continuity tests using a megger tool, along with phase identification and sequence verification, all documented in the AC cable test report. Next, earth resistance and bonding are tested by measuring the earth pit resistance and verifying bonding continuity, supported by an as-built earth map, with results compiled in the earth test report. Then we check the CT ratio and polarity through primary or secondary injection methods or other approved CT test procedures, recorded in the CT test sheet. For protection, we simulate various relay and breaker trips before energization, including functions like 27, 59, 81O, and 81U, ensuring protection systems operate correctly. These results go into the protection static report. Finally, we verify monitoring systems by checking loggers, meters, weather stations, PPC, cameras, gateways, and platform tags, with findings summarized in the point-to-point report. This comprehensive testing ensures all safety and performance measures are thoroughly validated before commissioning. This slide outlines the critical steps involved in the startup test and first energization for the rooftop solar PV system. First, we ensure readiness by completing the CXL2AB phase, confirming all preliminary checks are done. Next, we secure the necessary energization permit to proceed safely. Then we switch the power flow through the LVMDP to MDB and finally to the ACDB, establishing the correct electrical path. We start the inverters one by one, carefully monitoring each one to avoid any issues. We verify that no abnormal alarms occur during startup, ensuring system stability. Finally, we document everything in a detailed startup report. Key acceptance criteria include grid voltage, frequency, and power factor within the approved protection settings, proper breaker operation with door closed status indications, successful inverter self-tests and MPPT tracking, and accurate monitoring data with correct timestamps. This thorough process guarantees a safe and efficient system commissioning. On this slide, we focus on the Site Acceptance Test, or SAT, for the CXL4 project, specifically within the testing and commissioning phase of our rooftop solar PV factory proposal. The SAT package covers several critical functional acceptance tests to ensure everything works as intended. First, the protection SAT verifies the trip commands for various protective relays, event logs, and reset functions. Then, the emergency shutdown, or ESB/RSD SAT, checks the emergency shutdown path and reset mechanisms where applicable. The Zero Export and PPC SAT involves simulating export conditions and verifying curtailment responses against the approved set points. For monitoring SAT, we verify the dashboard functionality, alarm systems, trend reports, user roles, and cybersecurity controls to ensure comprehensive operational oversight. Lastly, The CCTV SAT confirms that coverage, recording, retention, motion and event detection, and secure access are all functioning correctly. Each of these tests is essential to guarantee a fully operational and secure solar PV system. Here, we're focusing on the integrity test and performance verification for the rooftop solar PV system proposed for the factory. The key formula for the performance ratio, or PR, is AC energy divided by the product of installed STC power and the plane of array irradiation adjusted by the standard conditions. This ratio helps us measure how efficiently the system converts sunlight into usable electricity. Now, the integrity check covers several critical points. The system must run continuously without unresolved alarms or abnormal trips, and the availability, meaning the actual operating time, must meet our agreed targets. Thermal imaging is used to ensure there are no critical hotspots on modules, terminations, or switchgear, which could indicate potential failures. We also sample 4 curves from representative strings and modules to confirm they're within expected tolerances. Before handover, any critical or A-level punch list items must be closed. Additionally, thermal inspection and cleaning play an important role in supporting accurate performance verification by maintaining system health. Overall, these steps ensure our system operates safely and effectively. On this slide, we're focusing on CXL6, which covers the handover and post-completion activities for the rooftop solar PV project. The handover includes several key deliverables to ensure smooth operation and maintenance. We start with the as-built drawings, which include layouts, single-line diagrams, string maps, cable schedules, earthing maps, and points of connection documents. Then, the O&M package provides everything needed for ongoing maintenance, such as manuals, spare parts lists, preventive maintenance schedules, warranties, data sheets, and an emergency plan. Training is also a major part of the handover, covering lockout-tagout procedures, system monitoring, alarm management, cleaning protocols, preventive maintenance, and emergency response. After completion, there's a structured review process at 30, 60, and 90 days to monitor production, performance reports, alarms, availability, and punch list closure. Lastly, annual readiness involves calculating performance ratios and availability, producing an annual report, and preparing a budget proposal for ongoing operations. All these steps together ensure a comprehensive and effective transition from construction to full operation. On this slide, we focus on the crucial topic of test instruments and calibration control, which is essential for ensuring the accuracy and reliability of our rooftop solar PV installations. We use a variety of instruments, each tailored for specific tasks. For instance, the digital multimeter checks polarity, voltage, and continuity, always backed by a valid calibration certificate to guarantee precision. The insulation resistance tester measures the resistance of DC and AC cables and strings, with test voltages and values carefully recorded. We also use clamp meters and irradiance meters to monitor string and operating currents, making sure to log time and irradiance conditions for accurate assessment. Earth resistance testers are employed to verify earth pit and system resistance, accompanied by earth reports that include weather conditions. The power quality analyzer plays a vital role by measuring point of connection voltage, current, power factor, and harmonics, correlating this data with the plant's performance. Thermal cameras help us conduct detailed thermography on modules, inverters, and panels, with emissivity factors and ambient conditions documented for thorough analysis. Finally, relay test sets are used for testing protection relays and trip circuits, providing settings and trip time reports. Maintaining proper calibration and detailed records for each instrument ensures our testing and commissioning processes meet the highest standards, directly impacting the success and safety of our solar EPC projects. Here we have the testing documentation matrix for the rooftop solar PV project. This matrix organizes the various commissioning levels from CXL1 to CXL6, each associated with a specific set of documents. At CXL1, we start with foundational materials like FAT reports, certificates, and vendor data sheets. Moving up, CXL2A includes detailed installation checklists and photo records, while CXL2B focuses on static testing reports such as insulation resistance and polarity tests. CXL3 covers critical documentation for energization permits and startup reports. Then, at CXL4, we document system acceptance tests, including protection and monitoring systems. CXL5 ensures performance verification through integrity runs and thermography reports. Finally, CXL6 wraps up all documentation with as-built drawings, operation and maintenance manuals, warranties, and training records, ensuring readiness for ongoing operation and maintenance. This structured approach helps maintain clarity and thoroughness throughout the commissioning process. Now let's focus on the post-completion phase, specifically operational handover, PM schedule, reporting, and the final evaluation checklist. This phase is critical because it ensures that all operations and maintenance activities are properly transferred and that the client has everything they need to manage the project moving forward. The client evaluation package plays a key role here, as it provides a comprehensive assessment of the project's success and readiness for full client control. This structured approach helps guarantee a smooth transition and lasting project success. On this slide, we focus on the post-completion preventive maintenance and service level agreement structure for the rooftop solar PV system proposed for the factory. Regular maintenance is crucial to ensure optimal performance and longevity of the system. The table outlines the key activities involved and their frequencies. Daily remote monitoring helps us instantly detect any outages, underperformance, or anomalies related to weather and data. Every 3 months, thorough inspections cover the PV modules, mounting systems, cables, and safety elements to catch any corrosion or needed cleaning. Thermographic inspections are carried out semi-annually or annually to identify hotspots or any abnormal heating that could signal potential failures. Annual preventive maintenance includes checking critical protection components like breakers, relays, surge protectors, and grounding systems to guarantee safety and reliability. Finally, monthly and annual reports compare actual system performance against expected benchmarks like P50 and P90, tracking performance ratio, availability, and any incidents or corrective actions taken. All this information is recorded and managed in the provided Excel sheet named post_completion_PM, which details the schedule, acceptance criteria, and key performance indicators. This structured approach ensures the system remains efficient and problems are addressed promptly. On this slide, we focus on the recommended spare parts and consumables essential for the rooftop solar PV system in our factory EPC proposal. First, having 20 spare PV modules ensures we can quickly replace any broken or defective panels, minimizing downtime. We also suggest keeping 1 spare inverter on hand, as this acts as a critical backup to maintain system availability. For panel protection and maintenance, items like MCCBs, indicators, fuses, and surge protection devices should be stocked according to the bill of quantities. Additionally, spare PV connectors and DC/AC cables are necessary to repair any damaged sections swiftly. To maintain monitoring reliability and security, spare power supplies for monitoring units, CCTV cameras, and fall arrest PPE are included, supporting safe operation and maintenance access. Finally, consumables like cleaning nozzles, valves, and pipes are vital to keep the cleaning system effective and ensure the overall system performs optimally. These parts together form a comprehensive readiness plan for ongoing operation and maintenance. Here we have the integrated project schedule for the rooftop solar PV installation at the factory. The timeline is spread across 17 weeks, covering all key work packages from engineering freeze to handover and project management activation. It's important to note the sequence of activities here, starting with engineering freeze, then moving into procurement and submittals, followed by safety controls and equipment installation including MMS and modules, DC/AC cabling, and inverter setups. Commissioning activities labeled as CXL1 through CXL6 are scheduled toward the end, with a critical pause for proof of concept shutdown and tie-in to ensure safety and system integrity. Actual dates are subject to confirmation based on material lead times, roof access, and client-approved shutdown windows. Commissioning can only begin once all static tests and energization permits are fully completed. This careful scheduling ensures a smooth and compliant project rollout. Here is our final submission readiness checklist for the rooftop solar PV factory EPC proposal. First, the proposal package includes a comprehensive PowerPoint presentation along with an Excel bill of quantities, both fully synchronized to ensure accuracy. The BOQ and bill of materials Excel files are intact, with new rows clearly marked and explained, and all formulas visible for transparency. Our project schedule is detailed within the PowerPoint, with work packages linked directly to the work management system and commissioning plan to maintain coordination. We've demonstrated our capability and execution method through documentation such as WMS, inspection test plans, risk registers, lockout-tagout procedures, and multiple commissioning levels, showcasing our full EPC competence. Additionally, the package contains all necessary layout, single-line diagrams, and concept drawings to provide a clear project visualization. We've also included technical data sheets and output from PVsyst and P90 analyses to back up performance expectations. Finally, the O&M proposal covers operational and maintenance costs, project management, service-level agreements, spare parts, and a post-completion review schedule to ensure long-term project success. This thorough checklist confirms we are fully prepared for final submission. Here is the final recommendation for the Rooftop Solar PV Factory EPC proposal. Our recommended baseline is a complete, safe, maintainable, and monitorable EPC scope. We suggest proceeding with the enhanced compliant EPC scope as the technical commercial evaluation baseline. It's important to approve the additional BOQ items highlighted in red, as these are essential for safe operation, monitoring, cybersecurity, zero export, testing, spares, and O&M readiness. We also recommend freezing the final price only after completing detailed engineering, vendor quotations, roof structural verification, AC route measurement, and approval of the POC shutdown plan. To ensure smooth evaluation, negotiation, and future contract management, the Excel workbook package will serve as the commercial and technical control register. The recommended decision is to approve this baseline scope, with a commercial reference value of just over 3 billion rupiah. Thank you for your attention. This rooftop solar PV proposal for the factory EPC is now fully prepared and ready for both technical and commercial evaluation. We've aligned the PowerPoint and Excel packages to the same baseline, covering the bill of quantities, work management system, inspection and test plans, risk assessments, lockout-tagout procedures, and commissioning levels from CXL1 to CXL6, ensuring thorough and consistent documentation.